Personality types have a significant influence on the way how the consumer behaves. Therefore, from the business point of view, that information can be used to increase click-through rates and consumer engagement with the online advertisement. It is not a very challenging task for a psychologist to prepare a psychological profile of a person, but in the high volume and dynamic online environment, it would be a too expensive and slow solution. Here, I will use a dataset collected through the Personality Cafe forum. The dataset comprises of 8,600 records of the last 50 comments left by the user of that forum, together with the labels describing the user's personality type, for example, INFJ. The goal is to predict the type using the post column. The dataset is highly imbalanced. To train a model that can generalize well, we have to make sure that the number of all labels are roughly the same. Here, if we use 4 outputs and a categorical cross-entropy loss function, we will make the model bias towards the INFP type. Instead, we will build a model for every pair of dichotomies. With that kind of separation, the lowest count on the labels, that is for sensing type, is 1197, which is a significant improvement on the 39 ESDJ records. Still, to prevent overfitting, we have to balance the dataset using undersampling. It will help us to deal with overfitting and biasing. Here we can also ponder over the metric we want to use to measure the performance. Simple accuracy score is not good enough. Without undersampling, betting always on intuitive gives us 86% accuracy score. Instead, we use area under curve receiver operating characteristic score, AUC ROC, as a measure of how well a model can distinguish between two binary classes. The bus balance dichotomies are thinking feeling and judging perceiving. My model using only 1500 tokens, but the length of the data in each row goes up to 10,000. Hence, in order not to waste any precious information, I split all the comments in a single row and concatenate them up to the total length of 1500. This way we can increase the number of samples fourfold, from 8,675 to 38,783. In the given dataset, the data is relatively clean. Every record comprises of the last 50 posts left by the user, with every post separated from the next one with 3 pipelines. Pre-processing involves replacing hyperlinks with what they represent, for example YouTube URLs with YouTube token, replacing picture links with the picture token, and other URLs with URL token, and removing all numbers. We also calculate the ratio of different elements in the sentence, for example emojis, exclamation marks, question marks, capital letters, unique words, etc. TF-IDF, short for term frequency inverse document frequency, as a numerical statistic that is intended to reflect how important a word is to a document in a collection of corpus. Variations of the TF-IDF weighing scheme are often used by the search engines as a central tool in scoring and ranking a document's relevance given a user query. Once we feed and transform the TF-IDF vectorizer, as a result we get a set of sparse vectors with a total length of 100,000. To be able to use the information, we need to use one of the dimensionality reduction techniques. The one that works with sparse vectors and is available in the sklearn library is the truncated SVD method. It allows us to reduce the size of the input vector from 100,000 to our arbitrary length, 500. Next step of feature engineering is creation of the proportions of different parts of speech in the post. I use NLTK's post tag function. As the result, we get a very detailed sequence of parts of speech tokens. I make it more concise by grouping them into 11 similar groups. The proportions of the parts of the speech seems to be strong features because Pearson's correlation between them is small. After the feature engineering stage, we get a set of vectors of 523 elements. We use min-max scaler to scale all feature values to be between 0 and 1. Then we save all fitted transformation objects TFI, vectorizer, truncated SVD, and scaler, so we can use them later in the inference stage. We feed the features into a simple feed-forward network with 2 hidden layers, followed by a batch normalization layer with very strong dropout to prevent overfitting, and one output with sigmoid activation to distinguish between 2 possible states. We use binary cross-entropy loss function and ADAM optimizer. This model has only 800,000 parameters. Before I chose feed-forward network, I also tried different configurations of recurrent neural network. Unfortunately, even after using different overfitting prevention techniques, due to the large number of trainable parameters, the network was still memorizing the training dataset and was showing poor generalization. I used 20% of the available data to validate the model. In this project, we have to train 4 binary classification models for 4 pairs of dichotomies. I compared the performance of the feed-forward network against way more sophisticated BERT transformer model. BERT is a language representation model. Unlike recent language representation models, BERT is designed to pre-train deep bidirectional representations from an unlabeled text by jointly conditioning on both left and right context in all layers. As a result, the pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art models for a wide range of tasks, such as question answering and language inference, without substantial task-specific architectural modifications. It is built upon transformers, which are a competing architecture to well-established recurrent neural networks, and are currently considered state-of-the-art for NLP. BERT model surpasses the feature-based approach. Unlike the simpler approach, no feature engineering is necessary. BERT uses already learned language model to learn more information about the texts. The downside is that it cannot be used in everyday settings because of the complexity. Neural networks record only slightly worse results with a model that can be used even on mobile phones. There is one interesting phenomenon I had noticed when I augmented the original dataset to 144,000 examples by limiting the length of the posts. After training, the evaluation shows inferior results. It can be caused by too high learning rate, but also it might be caused by the fact that curated Wikipedia articles and books, which were used to train a BERT model, have much more quality than the internet fora. Therefore, the language model is different to the publicly available one. Still, it is much better than guessing, and therefore, in the hands of talented marketing people, it can be turned into profit. Once all the models are trained, I built a Docker container for each of them. The role of these containers are to transform the input text and return predictions. The return type is the one which got higher prediction. The containers are controlled by Flask. Node.js backend is responsible for distributing the query to all model containers and collecting all the results before returning them to the user. Node.js allowed me to get asynchronous responses. Without it, we would have to use blocking methods to receive the predictions, which would increase the waiting time fourfold. Once the containers are ready, we can build the Kubernetes pod and deploy the model in the cloud. I use Kubernetes cluster I'm most familiar with, which is Google Cloud Platform. The front end is operated by JavaScript running on the client's web browser. The complete code with information how to build and deploy it is available in the GitHub repository. Thank you very much.